Alright guys, so to conclude our acceleration unit, we're going to actually work on some word problems. Now, if you study physics somewhere else or you look online, most of them will point you to more of what we're doing today. Now, I teach this class a little differently. I teach it using graphs first, and then I show you the equations because these equations come from the graphs. So if you type into Google kinematic equations, you'll get these four equations that will pop up. So the first one is x is equal to 1/2 at squared plus v naught t plus x initial. So I'm going to read out what all these variables mean. X, final position, a, acceleration, t, time, v naught, whenever you see the 0 in a subscript, that means initial, so initial velocity, t is time again, x naught, initial x. Sometimes you might see this formula written as delta x is equal to 1/2 at squared plus v naught t, and that x naught was subtracted over because, delta x equals x minus x naught. So sometimes you'll just see things kind of scrunched together. They're both the same thing though. The next equation, and I'll refer to these like 1, 2, 3, 4 several times. So for my test, I give you these equations, but you'll probably end up memorizing them anyways. So A, the second equation is acceleration is equal to v final minus v initial over time. Sometimes you'll see it written as delta v over t. You might recognize this one in a graph. Here's another equation. V final squared is equal to v initial squared plus 2a delta x. Sometimes that delta x is written out as x minus x naught. And then the fourth equation is delta x is equal to v final plus v initial over 2 times t. So these are our four equations that I'll be referring to. Sometimes you can subtract two of the same variables to be like delta x or delta v. Either way, they're usually referring to the same thing. Now, where these equations come from, they come from the three main types of graphs you'll see in acceleration units. So, for example, this object that's speeding up in the positive direction, these are all of its graphs, and I'll try to show you where these equations pop in. And actually, I'll draw this one. Well, I'll draw it like this. So, all right. So this object here, this is an object speeding up in the positive direction. This looks like almost like a quadratic function that you would have in algebra 2. Well, I'm going to point you to this equation here that is kind of represented with this here. So the way the curve opens up is determined by this 1/2 a. And basically how fast you're kind of going at the start is v naught t, and then your x initial is how high up you are. So basically what I'm trying to tell you is that all that stuff you're learning in algebra 2, you can bring it back into physics if you want. Generally, physics problems, you don't need to fully graph them out, but you have that option here. All right, the next graph. So a is equal to delta v over t. This is just the slope formula for this. So if you remember, the acceleration is the slope of this vt graph. That's where that comes from. Delta x, so equation 4. I'm jumping past equation 3, but equation 4 comes from the area. Now you might say, well, wait, the area is 1/2 delta v times t. So how is it this? So if you might recognize your shape formulas, this is like a hidden trapezoid formula. Now, if you have an object that's moving like this, well, this formula will still work. It essentially is still your 1/2 base times height kind of formation. But imagine you're actually going this fast. So now your area includes like this rectangle with the triangle. So this takes both of that into account. Now the third equation, I think we'll see it used in some problems later on, and I'll kind of show you how it pops up in those equations. But it's a little bit more algebraic, I have to show you. You need pretty much numbers to show that's happening. All right, so let's see how we're doing on time. All right, we're doing pretty good. I'm going to go through the first problem. So, and actually before I do that, I'm going to go over one more thing. So I'm going to make some room. Let me move this guy. All right, so these 4 equations. Why do we have 4 equations? Well, I'll give you an algebra kind of tip. As many equations as you have, you can solve for that many unknown variables. So 4 equations, I can afford 4 unknown variables about a problem. Well, what are my available variables? So I'm going to list them all out below here. You've got your position one, so x final, x initial. You've got your velocity terms, v final, v initial, and then you have acceleration, and you also have time. So we have 6 variables. This is actually working in our favor. If we know 2 things about a problem, we can actually probably solve it all. So what variables are missing in each of these equations I'm going to look at. So this one, I have all of them except v. All right. This equation, I'm missing all of them except x. Sorry, I have all of them, but I'm missing my position terms, x and x initial. All right, this one, I'll let you kind of look at it. What are we missing? T. And this one, we're missing A. Now, one thing to note, I've got 5 missing variables across these equations, but I have 6 of them. So one of them actually is in every one of these. And what that means for you is that you should probably solve for that missing variable every single time. That variable is v initial. V initial is very important. I would say v initial and acceleration are probably the 2 most important terms, but you pretty much always need v initial and then some other term, and you might be able to solve pretty much this whole problem. So hopefully those equations, I don't like teaching them so that people think they just come out of thin air. These come from Isaac Newton. Isaac Newton made these graphs. He was trying to describe, this world in a simpler way. So he made these graphs, and from those graphs come these equations. So we can sometimes shortcut these graphs. I still think you should make the graphs because the graphs help you think about what's happening in the problem and helps you avoid some easy mistakes if you're just reading what's happening in the problem. I'll do this first problem here. So we get a poorly tuned geometro can accelerate from rest to speed to a speed of 28 meters per second in 20 seconds. What is always a good practice is to list out any variables we're given. So I see, okay, 28 meters per second. So it's accelerating to a final speed of 28 meters per second. I also see, t is equal to 20 seconds. And at 20 seconds, I should be at 28 meters per second. Now, those are the only numbers I see, but sometimes they give you some more information. Rest. And this is a very common thing in these problems. They will tell you a term without telling you the number. I can assume, okay, well, for starting at rest, that means my initial velocity is 0 meters per second. And actually, there's another thing I can assume. I can assume that I'm going to travel a certain distance. I don't really have any position terms here. So I'm just going to make it easier. I'm going to say x naught is 0 meters. So what may have seemed like, they only give us 2 things here, we actually really have 4. And the only things we're missing at this point is acceleration and final position, which are the 2 things we're trying to look for here. Well, anyways, let me try to solve this problem again. So VT, I'm making a graph. Now, I got from rest to 28 meters per second. That means I'm starting at 0 meters per second. I'll end at 28 meters per second, and it will take me 20 seconds. So, assuming we're accelerating linearly, this is going to look like this on this graph. So I'm speeding up in the positive direction. Now, if you've been following along, then you know how I can get acceleration from this without even using one of these fancy equations over here. I'll just use, A is equal to delta V over T, which is going to be, I go up 28 meters per second over 20 seconds. That's going to give me 1.4 meters per second squared. So that's my acceleration there. Now, I would argue, hey, maybe we didn't need to make this graph at all. Maybe there was an equation that could have worked. And look at that. There's actually an equation that looks just like it. And why does it look just like it? Because it comes from this graph. So this is why I always emphasize to many people when they're teaching physics is that don't just jump straight to the equations, learn how the graphs work, and that's where the equations come from. So let me say I use equation 2. I have A is equal to V minus V naught over T. Well, that's going to be 28 minus 0 over 20. And look at that. I mean, it's the same thing, 1.4 meters per second squared. Very good. All right. Hopefully no confusions on part A. Let me do part B. All right, so part B, we have, they ask us the distance does it travel in this time. So as we know from all the previous stuff, area under a velocity time graph will get me the displacement. And in this case, it's going to be 1/2 base times height, which will be 1/2 times 20 seconds times 28 meters per second. Now, 1/2 times 20, that's going to be 10 times 28, that's going to be 280 meters. All right, that's pretty good. But what if, instead of using this graph again, I instead use one of these equations? So I can use equation 4. So I look over here. Chances are, because I found acceleration with 1, I'm not going to use it. So I won't look at 2. I look at 1, 3, and 4. Well, 4, has delta x. So let me try to use that. Delta x is equal to v plus v naught over 2 times t. And in this case, that was 28 plus 0 over 2 times 20. And what I end up getting is 14 times 20, and that equals 280 meters. That number should look familiar because it's a number I got before. So once again, I've proven these equations work. I mean, I told y'all this is the area from a VT graph, so it should work, right? They're derived from the same stuff. Now, what if I pick the wrong equation, which there isn't really a wrong equation, but let's talk about it. I pick equation 3. I'm going to walk us through. V squared is 28 squared. I know that from the problem. V naught squared, 0 squared. I know that from the problem. 2a. Now, I know a is 1.4, but I didn't know that at first. I had to solve for that variable, and then I have delta x. If you have 2 unknown variables, you can't use that equation yet. You have to solve at least one of those variables to solve the rest of the equation. So if I were to use 3 and you'd see a similar issue in 1, both of them you end up needing a to solve for anything involving position. So what I'm trying to tell you is, yes, it's possible to solve this stuff later on, but there's usually an easier equation to solve things before. So if it's taking you 2 or 3 steps, there's a good chance there's at least another equation that will solve it in 1 step. All right, so I'm going to pause the video here, and I'm going to task y'all with trying to solve the rest of these problems. And my advice is always make at least a VT graph. And why I say a VT graph is because a position time graph, although it shows you how an object's moving, which is nice, it is actually very unwieldy. You can't find the velocity easily. You'd have to take tangent slopes, or you'd have to mess around with average velocity. An acceleration time graph can show you how an object's motion is changing, but it really isn't good for displacement. A velocity time graph is nice because you can either take the slope of a graph, you can take the slope to find out the acceleration, or you can take the area to get the displacement. And before I send you off, I'll draw this graph for you. So I have a car that has a speed of starts at 30 meters per second, and it ends at 14 meters per second. And this takes 6 seconds. So I'll let you guys decide how you want to solve this, and I'll see you next video, and we'll solve this problem.